Okay, good morning, everybody. So for this week, we'll start talking about further applications of derivatives. I look at the section outline and it looks like it will revolve around optimization, differentials, and L'Hopital's rule. So these are just other things to which we can apply the concept of derivatives, okay? But before we start with the worksheet, just a reminder, you have some quizzes due this week. Plus, on November 20th, test number 4 will start. So it's going to be on the 20th to the 21st. But the scheduling for test number 4 will start, actually already started last Friday. So kindly schedule your exam then. And then I think the practice test would be available sometime this week. So maybe since this week and actually also next week would be full up submissions or assignments for you guys. I encourage you to start answering the practice test as soon as it becomes available. Right? Maybe we can talk about the practice test sometime next week so that you'll have some added preparations for test number 4. All right. So, but before we proceed to the worksheet, let's just have the first set of popper questions for this week. So, ready, guys? Maybe I'll start with 4 questions today, 3 questions on Wednesday, and 3 questions on Friday. All right. So here's our popper for this week. Hopefully you can see my screen. Okay, there you go. Okay, question number 1. Oh, you don't see question number 1? Let me. Okay, now can you see it, Daniel and Arian? How about the others? Can you see question number 1? Okay, good. Okay, for those who have seen the question late, kindly take a snapshot. I'm going to go to problem number 2 in about 15 seconds. Okay, let's go to problem number 2. Okay, now I'm flashing question number 2. Hopefully you guys can see it. 15 seconds for problem number 2. Okay, let's have problem number 3. Okay, 15 seconds for problem 3. Now let's have the last problem for today, problem 4. Problem 4 is quite similar to problem 3. It's just that the assumption and the conclusion were reversed. So basically, problem 4 is the converse of the statement in problem number 3. Okay, if you want, guys, I can go back to all the questions to give you maybe 10 seconds to make a screenshot of all of the questions for today, just in case you didn't see all the problems. Okay, 10 more seconds for problem 4, then I'm going to go back to the other questions. Okay, let me just give you a couple of seconds to screenshot the previous questions. Let's have problem 3. Okay, now I'm going to problem 2. And lastly, here's problem number 1. Okay, don't forget to encode your answers to CASA. This would be due on Saturday, November 14th. All right. Okay, we'll have the remaining 6 problems on Wednesday and on Friday. Okay, now we'll go to worksheet number 17. I already uploaded a blank copy on my website. Download it from there in case you want to work on it independent of what I'm doing here. But of course, I will again upload the annotated versions of the files later today. Okay, sorry. So again, this worksheet is about further applications of derivatives, and there are 3 main topics here. Number 1 is optimization. Second is differentials, and the third one would be on L'Hopital's rule. So the first one is about optimization, but basically This is similar to what we have seen before when we're looking for the global extrema or the local extrema of a functions. We went through a certain process, right? First, we took the derivative, then looked for the critical numbers, and then verified if indeed we have a local max or a local min, or if we have a global max or a global min. Now, we will apply the same process, essentially the same things, but this time the questions will be phrased in terms of practical applications or word problems. So we have a word problem, then we'll try to have a mathematical formulation for that optimization problem. But after we have that model for the optimization problem, then what we'll do is to apply what we learned before insofar as finding the extrema of functions are concerned. And then right after we compute those extreme values, then we'll write the appropriate conclusions to answer what the problem is asking for, right? So let's try these examples. I guess there are 7 examples here. Let's try to answer as many as we can. Oh, by the way, this worksheet was suggested for this week and next week. So don't worry if you browse through it and you see there are 14 pages. So if we will not be able to finish all of these this week, then we can we can continue next week. But I'm thinking maybe next week we can also focus on the practice test number 4. So what I'm going to do is to try to finish as many problems as we can this week, so we can reserve as many times as possible next week for practice test number 4. Okay, I hope that's okay with you guys. So let's start. Problem number 1. For number 1, we need to find the greatest value of the product xy of real numbers x and y, such that x plus y is 100. Maybe the first step is to write the objective function. So what is the objective function? The objective function is basically the function that we want to maximize or minimize. So it might involve some formula, say for the area, for the surface area from the volume, or those usual formulas you meet from geometry. Sometimes they are just some relations between the variables coming from algebra and so on. But another thing is that you will see that sometimes that those formulas or the objective functions are usually written in terms of 2 or more variables. But insofar as Cal 1 is concerned, we don't know how to work with functions involving 2 or more variables. So aside from identifying the objective function, we should also identify what are the constraints. But for now, you can think of the constraints as the relationship between the variables in the objective function. Right? And again, we only need the constraints if there are 2 or more variables involved in the objective function. Because if the objective function only involves 1 variable, then you can apply our basic tools on how to find the local or the global extrema we learned from chapter 3, right? So, but in the presence of 2 or more variables, we need to identify the constraints. So what relates those variables together, and what we need to do is to compute 1 variable in terms of the other, so that the objective function will be expressed explicitly in terms of a single variable, right? So let's look back at the problem. Now the problem asks for the greatest value of the product xy. So that tells us that in this problem, we want to maximize the product xy. So here, I want to maximize the objective function f, which is the product of x and y, right? But again, the problem here with this objective function, this is the correct objective function because this is what we want to maximize, right? So because we were told to find the greatest value of xy, right? But the problem with this is that we have two variables, x and y, involved. So we want to write the objective function in terms of only a single variable. The only reason we want to do that is because we don't have the tools currently to work with two or more variables. But I guess in calculus, calculus 3, or even in the latter part of calculus 2, you will learn how to deal with functions of more than one variable, right? But for now, we don't have that capability, so we need to identify the constraint. So we are maximizing this objective function subject to what condition? Well, this would be the constraint. And if we look at the problem, what would be the relation between the variables x and y? So we are maximizing the product xy of two numbers x and y such that x plus y is equal to 100. So I can consider that as my constraints because that bounds x and y, or that gives us the relationship between the two variables x and y. So I can write this as, I can write it here, right? So subject to x plus y equals 100. But this tells me, okay, so if x plus y is equal to 100, then I can write y as 100 minus x. And what I'll do is I'll use this constraint and plug it into my objective function, and you will see what will happen. The function f can be written in terms of the single variable x, right? So now we can say that this optimization problem is equivalent to maximizing f of x. Now I'm sure that f is a function of a single variable x, which is x times y, but y we know from the constraint is 100 minus x. Okay, but I can bring it a little, I can do a little algebra here and write it as 100x minus x squared. And that's our objective function. Now, what we need to do would be to apply the tools that we learned from chapter 3 on how to get the maximum of a function f, right? Remember, the first step is to find f prime, right? F prime of x is 100 minus 2x, okay? And we do that in preparation for the second step. If you remember, the second step is to find the critical numbers, right? And to find the critical numbers, what we do is we either equate f prime to 0 or find when is f prime undefined, right? But if you look at f prime is a polynomial, so it will be defined everywhere. So the only critical numbers will be coming from setting f prime of x equal to 0, right? So f prime of x equals 0 means 100 minus 2x is equal to 0. Then we'll solve for x. So we get negative 2x equals negative 100. So x is equal to 50. Okay, so now we know that 50 is a critical number. All that remains to be seen is that will 50 give us an absolute will give us a maximum or a minimum, right? But maybe I'll put that as an explicit third step. Check if Cn gives a max or a min. Okay, and this is a step most students forget. Once they get only one critical number, then they just say, oh, my final answer here is x equals 50. That's wrong, because remember, a critical number can give you a local maximum, it can give you a local minimum, or it can give you neither a maximum nor a minimum. So that means we need to go through the third step and to check whether it gives us a max or a min. But before going there, I see a question from the chat. Where again did you get the extra x to factor in? Where is that? Do you mean Daniel here? In the function f? Yeah, so that came from the objective function. Remember, the objective function is x times y, right? Because we're maximizing the product. Now it's x times y. The problem with that objective function, it involves two variables. So I want to eliminate one of the variables. And I decided to use the constraint in order to solve for y in terms of x. So basically this x was copied over from the objective function. And the second factor is just from plugging in y equals 100 minus x coming from the constraint. And that gave me the objective function in terms of only a single variable x. And then I took the derivative, critical numbers, and now I'm going to check whether I have a maximum or a minimum. Okay, good. So now, how do we check if it's a maximum or a minimum? Well, you have two options, right? Because the problem here is what would be the domain of f, or what are the possible x and y's? Well, the possible x and y's are any real number, so that's an unbounded interval. So we cannot use the extreme value theorem. So we have two options here. Either use the first derivative test or the second derivative test in order to check whether we have a maximum or a minimum, right? So it depends on you which one to use. But here I prefer to use the second derivative test because finding the second derivative is very easy. F double prime will just be -2. And remember what the second derivative test tells us? The second derivative test tells us that if you plug in a critical number into the second derivative and the answer is negative, then you have a maximum. And if you plug in the critical number to the second derivative and you get a positive number, then you have a minimum, right? But here I have f double prime equals -2. I'll plug in the critical number 50, and it doesn't matter. It's still -2, which is less than 0. So we'll get a maximum, right? Because the second derivative is negative, right? And then this is the additional step when working with word problems. Make sure to answer the question. So what is the question here? The question is find the greatest value of the product xy. So what would be the maximum product? Well, here we can say that the product is maximized when x equals 50, right? And what would be the y value? If x is 50, then y will also be 50, right? Because the constraint tells us that y equals 100 minus x. So that's 100 minus 50. So y is equal to 50. So the maximum product is 50 times 50, which is 2500, right? So basically, the important thing here is you mentioned that the maximum product is 2500, okay? Because if you'll stop here, or even here, you were not able to answer the problem completely. So you'll get probably some deductions. So make sure to go back to the problem and make sure to answer what it is asking for. Okay, is that clear? Any questions? Again, the only new thing here is that we need to identify what would be the objective function. And in some cases, we also need to find the constraints. So I guess that's the difficult part, but the rest of the steps would be would be exactly what we did from chapter 3. When we look for the local maxima or local minima, or global maxima or global minima of certain functions. All right? So nobody's reacting, so I'll take that as an indication that you don't have any questions. Maybe you're still having the weekend hangover. Okay, let me proceed to problem 2. Problem 2, suppose you want to fence in a rectangular shaped region along the straight edge of a river. The side along the river doesn't need to be fenced. In addition, the region will be subdivided into 2 parts. The fencing material that will be used for the 3 sides that are perpendicular to the river costs $5 per linear foot, and fencing for the other side costs $10 per linear foot. Suppose you have $450 to spend on fencing. Find the dimensions of the total region that will provide the maximum area. Okay, so I guess here we need to have a rough sketch of the situation just to make the modeling easier. So we have a rectangularly shaped region along the straight edge of a river. So say the river is here. Okay, so you have a river here, and then you have a rectangular shaped region over here. Assume that's a perfect rectangle. And then the side along the river does not need to be fenced, so no fencing is required along the river. And in addition, the region will be subdivided into two parts. So maybe I'll have here the other division. And the fencing material that will be used for the three sides that are perpendicular to the river costs $5 per linear foot. So the fence here, here, and here will cost $5 per foot. And the fencing on the other side costs $10 per linear foot. Now, so here, let's identify what are the objective function and the constraints, right? So here we want to maximize what? We want to maximize the area, right? So we want to maximize the area of the enclosed region. Now, what's the formula for the area? Well, the area is length times width, right? So let's call this the length. Let's call this the width, right? So the formula is length times width. The problem with this is there are two variables involved, L and W, and we don't have, again, the tools right now to solve optimization problems involving more than one variable. So we are hoping that there is a constraint that will give us the relation between L and W, right? But what are the constraints here? Well, the constraint is that we have $450 to spend on the fencing, right? So, and then the cost per foot of fencing on the sides of the rectangular plot vary depending on where the side to be fenced is located, right? So, but basically here, uh, those highlighted in yellow, what would be the total length for the fencing needed there? So remember, I called this length L, right? So I'll have an L here, another L here, and another L here. So that's a total of 3L feet to be fenced using material that costs $5 per foot. So this is 3L foot times $5. So that's the total amount needed to fence those highlighted in yellow. Plus, the one highlighted in red is parallel to the river, and the problem says that it will cost $10 per foot to fence it. So that's gonna be $10. But how long is that? Oh, I call that W. So that's gonna be 10 W times 10. And the total amount should be equal to $450 according to the problem, right? So I'll just simplify the constraint. So this is 15L plus 10W equals 450. And now you can select which variable to express in terms of the other. So here maybe I can express W in terms of the length. So here I'm going to have W equals 450 minus 15L over 10. So that would be our value for W. Okay. Now, so we can write the objective function as A equals length times width, but we know that the width is equal to 450 minus 15L over 10. Okay, so this would be what? This would be 45L minus 3 over 2L squared. Is my simplification correct? So that's 450 divided by 10, so that's 45 times L. Then 15 over 10 is going to be 3 over 2 L times L, so L squared. All right. Okay, now we have the objective function written in a nice form. And by nice, I mean only in terms of a single variable. Now we can take the derivative of the objective function. That's our first step. So that's going to be 45 minus 3L, which is again a polynomial in L. So the second step, finding the critical numbers, would be easy because we just need to equate the derivative to 0. And that means we have 45 minus 3L equals 0. That means we'll get 3L, or negative 3L equals negative 45. So L is equal to 15. So the best guess we have is that the length L equals 15 would be critical because it will give us either a maximum or a minimum. But there's a slim chance that that won't give us neither a maximum nor a minimum. So let's check if indeed this will give us a maximum. Check if Cn gives a maximum. Right? And again, you have two options. Use the first derivative test or the second derivative test. But since A prime is just a polynomial, computing for A double prime wouldn't be that hard. So I'll choose to use the second derivative test. And if I do so, this would be negative 3. That will imply that if I plug in the critical number, I'll get negative 3 still, and that is less than 0. So L equals 15 gives a maximum. Right? And then we'll go back to the problem and see what it is really asking for. It's asking for the dimensions of the total region that will provide the maximum area. And aside from the dimensions, meaning the length and the width of the region, then we also want to see what's the maximum area. So we can say that therefore, the dimension or the dimensions of the region with the largest area are, so the length would be 15 feet by what would be the width. But the width, remember, is computed this way, 450 minus 15L over 10. So by, maybe we should compute that before we write the conclusion. So here W equals 450 minus 15L over 10. So that's 450 minus 15 times 15 over 10. That's 450 minus, what is 15 squared? Is it 225? Yeah, it's 225 over 10. So that's going to be 225 over 10. So that's 22.5 feet. Right? So its area is 15 times 22.5, which is 337.5 square feet. Okay, guys, any questions with that? Guys, are you still there? Okay, thanks for answering, Francisco. Everybody is following. Okay, good. Right. Because usually students hate word problems. And actually, that's sort of a paradox to me because whenever you meet students and you're teaching them this level of math, they will say, where will I use it in real life? What would be algebra and calculus for in our daily lives? But when you give them this textbook word problems, though they are still theoretical in nature, but they are a good indication of where you can use these concepts in real life. And they usually hate word problems. I guess the hatred sort of comes from the difficulty they encounter in analyzing this kind of problems, right? But I guess it would be, well, I guess the key here is to understand the problem very well and have at least at the back of your minds those basic formulas from geometry, from algebra that can help you form the right objective function, okay? And usually drawing a picture of the problem gives us a good understanding or have a good idea of how to do the modeling of the word problem, right? So let's look at this one. And I guess this is quite similar to what we had before. So let's see, a man wishes to have a vegetable garden enclosed by a fence in his backyard. The garden is to be a rectangular area of 60 square feet. Find the dimensions of the garden that will minimize the amount of fencing material needed. So he has a rectangular piece of land that he wants to turn into a vegetable garden, which is to be fenced, right? And this has an area of 60 square feet, right? And then we want to find the dimensions of the garden. So we're looking for the length and the width of the garden so as to minimize the amount of fencing material needed. But so that's a clue. So that's our objective function. We want to minimize the amount of fencing material needed. And like problem number 2, there's no costs mentioned in the problem. So we can assume that here we don't care about the cost, but we're just looking for what would be the amount. What would be the minimum amount of fencing material needed. But the fencing material will just be the sum of the lengths of the dimensions of the garden, right? So basically, if you remember, that's what we call perimeter in geometry, right? And the perimeter is just the sum of all the sides of the rectangle or the lengths of the sides of the rectangle. So in this case, it's going to be 2 lengths plus twice the width, right? So even though if you forgot that it is called the perimeter or what's the formula for the perimeter, sometimes intuition will guide you to have the proper model, because here I just knew I want to fence it. So I just need to measure how long is this, which is L plus W plus another L plus another W for a total of 2L plus 2W, right? But again, the objective function we have here is written 2 variables. So we need to look for a constraint that tells us the relation between these 2 variables. So these 2 variables are connected with the requirement that the area should be 60 square feet. So we can say that such that the area is 60 square feet. But remember, the area is computed as the length times width. Okay. So from that information, I can solve for one variables in terms of the other. So for instance, here I can say, oh, the length can be written as 60 over W. Okay. So now we can write the objective function P in terms of the single variable L, or sorry, W, such that 2 times L, but L is equal to 60 over W plus twice W, right? We're going to rewrite it as 120 W to the negative 1 plus 2W. Okay, so that's our objective function. We want to minimize this. The first step is to find the derivative, right? So P prime of W would be negative 120 W to the negative 2 plus 2. Okay. The next, we'll find the critical numbers, right? So here, We can look at P prime as what? Negative 120 over W squared plus 2. So the first set of critical numbers can be obtained by putting F prime equal to 0. That means we'll have negative 120 over W squared plus 2 equal to 0. That means we'll have negative 120 over W squared equals negative 2. I can multiply both sides by negative W squared. So we'll have 120 equals 2W squared. And then I can divide both sides by 2. So we'll have W squared equals 60. That means W is plus or minus root of 60. Okay, and we can write that as what? We can write W as, okay. I'll leave it in that square root form because I guess it would be easier to manipulate it there. But actually, we can eliminate one of the critical numbers here because negative root of 60 doesn't make sense insofar as the problem is concerned, right? Because W is a measurement of the width, right? And the measurement of the width should be non-negative, actually positive. So we can say that, okay, W should be equal to root of 60. Okay. Now the other source of critical number, just to remind you guys, is when is F prime undefined. But if you look at P prime rather than F prime. If you look at P prime, be undefined when W is equal to 0. Oops. So W equals 0 might be a critical number, but a quick check, does W equals 0 make sense insofar as the problem is concerned? Remember that W is a measure of the width of the garden. So if W is equal to 0, then that means you won't have a garden at all because the width equals 0 means you won't have any area, right? So that means, and actually if you look at P, or our objective function over here, it would be undefined as well when W is equal to 0, right? So we can say that we can also ignore W equals 0 because it won't be a critical number because it is not in the domain of P. But it is not in the domain of P, right? Okay, so that means we only have one candidate here. Our only lone candidate is root of 60, right? That's the only remaining critical number that we have after eliminating those that doesn't make sense insofar as the problem is concerned, right? So now we need to check if the critical number will give a minimum. Because remember, our goal is to find the dimensions that will give us the minimum or that will require the minimum amount of fencing material, right? And again, I'm going to use the second derivative test. So I need P double prime. P double prime would be, okay, so it's going to be 240 W to the negative 3, okay? So that's a P double prime. And then if I plug in root of 60, okay? Actually, you don't need the exact value. All you need to observe would be the sign. So if I have root of 60, I know that's positive. Positive raised to the negative 3 will still be positive. Times 240, it's still positive. So I don't care what the exact value is. All I need to know is its sign. And I know it would be greater than 0. So we'll have a minimum. Okay. And let's go back and see what was asked in the problem. It's looking for, again, the dimensions of the garden. So I need both the length and the width, right? So if W is 60, oops, or root 60, then the length, according to the constraint, was 60 over W. This would be 60 over root of 60, but this would be 60 root of 60 over 60, which is also root of 60. Good. So the dimensions that will require the minimum fencing material are root 60. What was the unit of measure here? Feet. So it's a root 60 feet by root of 60 feet, right? Which is basically a square. So usually squares are the most economical types of rectangles. So yeah, so it's not completely surprising that the length and the width are equal here, because again, squares usually are the most economical type of rectangles. Well, it might be different if the price for fencing for the length and the width are different from each other, but in a more general sense, without any additional constraints, usually if I'm going to bet, I should get a square for an economical rectangle, right? Okay, is that fine? Can we move on to problem 4? Let me just check the remaining problems while you're deciding, okay? Okay, yeah. Let's try problem 4. So number 4, a closed-top rectangular box with a square base will be built to hold 1,000 cubic feet. What should be the dimensions be in order to minimize the cost of material used to build this box? Okay, so this is a very interesting problem because you can think of it as if you are the CEO of a, say, a juice company, and you are asking your manager to say, how should we create our juice carton in order that it will hold a certain volume, but we will require the minimal surface area or the minimal cost to produce the box, right? Which is a very interesting problem because this is very close to reality, right? So let's see. So we have a closed-top rectangular box. So pardon my drawing here. I'm not good at drawing 3D figures. So you'll need to use your imagination over here. Okay. So imagine this is a box. Okay. Then it's a closed top, so that means there's also material needed to build the top, right? That's what being a closed top rectangular box means. So there is also material on the top of the box. Then what else? It has a square base, so it should have a square base. So if I'll call this X units, this side should also be X units. Again, because it should have a square base, okay? And it is to be built so that it holds 1,000 cubic feet. So that means the volume should be 1,000 cubic feet, right? So that's the amount of material that should go inside a box. Now, what should be the dimensions in order to minimize the cost of material to be used? So we want to minimize what? We want to minimize sort of the surface area, right? So I'll call it S, the surface area of the box, because that's the amount of material needed to construct the box. Now, it would be great if you know what is the formula for the surface area, but in case you forgot, no problem here. So we can compute it manually. The surface area is just the sum of the areas of the 6 faces of this box. So if you look at, say, let's first look at the top and the bottom. So if I look at the bottom and the top of the box, so those highlighted in yellow, they will have equal areas. So I can just multiply the area of one of them by 2, right? So twice the area of one of them. But what's the area of one of them? Oh, I know that this is x units. This is also x units. So the bottom will have area x squared. The top will also have area x squared. So that's 2x squared. Plus, what will be the area of the remaining 4 faces, right? So maybe I need to introduce a variable here for the measurement of this guy. Let's say that is y units, okay? So let's measure the area of this side, the red side. Well, that red side will have area x times y, right? And then that will be the same as the area of this side over here. That's also x times y. So I have 2 of them now. But the front face will also have the same area because it's x times y, as well as the back end. All right? So that means that there would be 4 xy's in the surface area. Okay? But again, this objective function involves 2 variables, and we don't want to do that. So we need to have a constraint. So subject to what constraint? We know that the volume should be 1,000 cubic feet, right? But what's the formula for the volume? Well, the volume is length times width times height. But if we put that in the context of the variables we used, so it's going to be x times y, okay? So that means the volume is x squared y. Now you can decide which variable to use here. You can solve for y in terms of x or x in terms of y, but you'll see that the more convenient choice is to write y as 100 over x squared. Because the alternative is to say that x squared is equal to 1,000 over y, then x squared, then x would be root of 100 or 1,000 over y plus or minus. Well, you can just say, oh, it should be the positive root because x is the measurement of a side. But you see, there's a square root. Oops. And we don't usually want to work with square roots. So that's why my choice here was to write y in terms of x. But there's nothing wrong using the other alternative. So you can also use that, though I don't want to work with square roots. So I chose this representation. And so the objective function s can be written in terms of the variable x as 2x squared plus 4x times 100 over x squared. Simplify, we have 2x squared plus 400 over x, or we can rewrite it as 2x squared plus 400 x to the negative 1. I did that in preparation for the first step, or the first calculus step. Hold on. Oh yeah, that should be 1,000. Thank you, Edin. 1,000, 1,000, and 4,000 here. Okay, I think that's correct now. Okay, good. Now we need to find s prime. S prime of x would be 4x minus 4,000 x to the minus 2, right? Then we need to find the critical numbers. Again, the first source is to just set x prime equal to 0. That means 4x minus 4,000 over x squared equal to 0. I'll continue over here. That means we have 4x equals 4,000 over x squared. Then I can multiply both sides by x squared, so I'll have 4x cubed equals 4,000. Divide everything by 4, so I'll have x cubed equals 1,000. And take the cube root of both sides, I'll get 10. Okay. And the other critical number is possibly will come from when is s prime undefined. Is undefined when x is 0, but this is not in the domain of S, right? Why is x equals 0 not in the domain of S? Because the problem will not make any sense if you put x equals 0. If x is equal to 0, then that means that the volume of the box will be equal to 0, and it doesn't make any sense, right? So we can disregard that. So we only have one critical number, x equals 10. Then we need to check if x equals 10 gives a maximum, or sorry, a minimum. Again, we can do so by using the second derivative test, but again, you can also use the first derivative test. So the first derivative test tells us this is 4 plus 8,000 over x cubed, right? But it's easy to see that if I plug in 10 here, I'll get a positive number, right? Because this would be positive, this would be positive, so I'll get a positive number. So, oops. So we'll get a minimum. And then look back at the question. What is it asking for? It's asking for the dimensions. So we need to give both x and y, right? So we solve for y, but y is equal to 1,000 over x squared. So we'll have 1,000 over x squared, but x is 10. So that's going to be 10, right? So the dimensions that will require the least material are 10, what was the unit of measure? Yeah, 10 feet by 10 feet by 10 feet, which is what? Which is a cube, which is not surprising because cubes are the most economical rectangular prisms, right? Absent any other special requirement. Okay. So sorry I took up more time than what we have, but hopefully this makes sense. So I'll leave you the option of whether do you want us to continue with the problems 5 and 6 on Wednesday, or you want to start with the next section here, which is using differentials. I guess it wouldn't hurt if we start with problems 5 and 6 on Wednesday, but you can already start working on it, and then we'll just start with them on Wednesday and continue on with other applications, okay? So again, I apologize for taking too much time today, but now you can go and rush to the lecture. Have a good day, everybody, and see you again on Wednesday. Have a good day.